The first presentation here would be made by Jeffrey Haemer with a presentation named Internet Services and How They Grew. Jeff, please.
You want to say something first?
Yeah, I want to say the following, that I insisted, I asked Jeff to come here because in some special moments he was here. So in '93, when we did the first conference here ever in Romania, and we were thinking that we will fail, he was here. And we had such big success that next year we had 600 visitors at the conference, which you may imagine that in 1994 was quite difficult. This was because he had a conversation with Tom Christiansen. He was in Moscone Center in San Francisco, and we talked from Cluj from '93 by a link provided by Liviu Ionescu by EUNET. And they asked if he can come also to Romania, and everybody was very enthusiastic in this moment. So I'm sure that if he starts this session, will have success with RITE.
Thank you. Oh, look, there we go. So I think that since a lot of this stuff is about internet history and it's about internet services and it's about all sorts of things, somebody needed to talk about internet services and applications, the layer up from that. And so I'm going to talk about where we've been and where we're going, and I'm going to try to make it fairly short because the conference is running a little long, right? So as to where we're going, that's easy. As to where as to where we've been, that's not so hard. As to where we're going, well, yes. Okay. Hi, I'm pretty qualified to talk about where we've been because I've been doing it for a really long time. I started programming in 1967. I taught courses at the University of Colorado using card decks, and so I tell people that when I started programming and teaching programming, we programmed by punching holes in little pieces of cardboard. And one of my friends heard me and said, "Really?" And I said, "Well, I think so. But it seems so unlikely that maybe I just dreamed it. I don't know. It just doesn't, it's so long ago and it just doesn't seem like that's possible." Oh, yes, thank you. But what comes next is a more interesting question. And so I thought about it very hard, and I can give a very precise technical answer, which is that I don't know, right? But I think that there are ways that we can get insight about what will come next, and that's by looking at the past. My experience is that when we're talking about computing, everything old is new again. I will talk about a particular example in a second, but George Santayana says that those who cannot remember history, who cannot remember the past, are condemned to repeat it. And I think that there's a converse to that, which is that those who can remember the past can figure out what to repeat. And so a nice example of that is when in 1967 or so, you had terminals. Anybody here ever see a terminal? Some of you, right? And the terminals were connected to a mainframe, a giant computer in a big room that was less powerful than my phone is. And you typed on it, and you all shared the same computer, but the thing that was sitting in front of you wasn't a computer. It was just a channel to a computer. And by about 30 years later, by 1993 or so, 1997, There was a company called Sun that has been mentioned here already. And Sun made the first really popular workstations, and they sat in front of you, but its philosophy, its slogan was that the network is the computer, and so their vision at the time was that although you had a computer in front of you, it was often a thin layer that was a way to access the internet. And that was because a bunch of things like FTP were around that moved data from one computer to another, or Telnet and RLogin that could move you from one computer to another. And that sort of went away, but there were client-server architectures. It was a big deal for a while. And today, we have Chromebooks and we have cloud computing, and we'll hear about cloud computing shortly, yes? Chromebooks are another Linux distribution, and they're really appliances. I own a Chromebook. In fact, in 2020, Chromebook sales surpassed MacBook sales. So it's a big deal. And here you're back to the idea that you're sitting in front of this thing, but really what you're talking to is the cloud. I made these slides on a Chromebook. And, okay, let me do this correctly there. So I was thinking about internet applications, and I realized that what the internet does is it erases things. One thing is that it erases boundaries. So I mentioned the fact that it erases the boundaries between computers, because you can log into different computers, and you couldn't when I started. It erases the boundary of data between computers, because you can move your data from one computer to another, and it erases the boundaries between people. And I'll give you two examples. I quit my job as a developer at Twitter about 3 years ago, and the thing up on the upper left-hand corner is Jack Dorsey's first tweet, in which he was putting up his first tweet, and now Jack has millions of followers, right? And then the second, that was, I think, 2007. The second is an email from me to Sebastian Saralunga, who is not here right now, but whom I met in 1993 in Cluj when I came over. And he was a student, and by 2004, he sent me email and said, oh, I have some invitations to give out for Gmail accounts, which was this new product in beta, and you could only get it by invitations. Would you like one? And so that's when I got my email account. I got it because I had a connection to Sebastian. I was obviously already exchanging email with him, just not Gmail. And this is the distinction between these two, although they're both things that connect people across boundaries, across oceans, across continents, is important. And Esther Dyson is going to talk about those next. And I think I won't telegraph her punch. I'll let her give it. But there we go. So what else has the internet erased? Well, sort of a lot. It's like, how many of you still buy newspapers and read them every day, or go out and look at the newspapers for what the weather's going to be? Me, I look it up on my laptop, right? How many of you keep maps in your car? A couple of you, but it used to be that we all did. And that's, the map industry has been erased. I've watched map stores close. How many of you own a multi-volume encyclopedia? I just look up things on Wikipedia, right? I get into an argument with somebody, I say, Alexa, what's the capital of Romania, you know? I actually own a printer, because I've made printers. I worked for Konica Minolta making printers for a while. But mostly people don't even bother. They just do things electronically, or they send it out to a print shop. How many of you have a phone book or have a landline? Some of you, it's the same, yeah, the same people who still own maps. My grandmother's phone number was 1 because she had the first phone. And now you can even take your phone from one place to another and keep your phone number, which in the US you didn't used to be able to do because the phone number was tied to a location. And that's all via the internet, of course. All of those phones. I worked making Android phones for a while, and the calls are all internet-based ultimately. That was actually, I think, originally the reason that Vint Cerf came up with TCP/IP was to make phone calls more secure and reliable. Come on. Now, obviously, I haven't talked about the ocean of different things, from ChatGPT to browsers that are internet applications, but that's because, you know, they give me 15 minutes. What can I do there? But it also erased another thing, which was privacy and security. Who here besides Mike can identify these two people? Anybody know who the person on my side of the slide is? Yes, okay, Adi knows. It's Eric Ullman, and he wrote SendMail, which used to transport all the mail across all of the Unix systems in the world. Oh, Adi, you can talk to Adi, and he will tell you about a story about how Eric saved him $5,000. He saved me a lot of work one time. I called him up and I said, Eric, I can't figure out how to configure my SendMail, and he just did it for me. But the guy on the left is Robert Tappan Morris, who wrote The Great Internet Worm in 1989 or something like that, 88. Was the first person to go to jail for, well, get convicted of internet crime of some sort, because the prosecutors in the government decided that they wanted to prosecute him for it. And he sort of did it by accident, actually, probably. He built it and then it got away from him by accident. But now we have spam, we've got viruses, we've got worms, we've got phishing, we've got all sorts of things that he was a pioneer for. And this picture, I took this picture at a Usenix Association event when he had just finished his community service. And then he became a professor at Harvard or MIT. MIT, yeah. So he's a smart guy. There, okay, so I'm gonna finish out with the story. And this is it's just a completely personal story, but I think it has a message. So on the last day of September, 30th of September, I got up in the morning and I looked at my phone. Actually, I wasn't even out of bed. I looked at my phone and the display said, in 17 minutes, you have an appointment to get your flu shot, your influenza shot, vaccination. And I went, whoa, I forgot about that. I put it on my calendar a month before and just completely forgotten, and I got up and my phone had looked in my calendar and was reminding me, helpfully. So I quickly got on my clothes, I ran to my car, I took my phone with me, and I said, give me driving directions to the clinic where I'm supposed to get this. And that was 2 towns away. And so I drove 2 towns away, following the driving directions of Google Maps. And on my way there, my phone which was sitting up on my dashboard, said, you have a text message from Ron Friedland. It's a guy I know in Oregon, which is a time zone away from me. Said, would you like me to read it to you? And I said, yeah, I would. So it read me the message. And then it said, would you like to reply to it? And I said, yes, I would. And so I dictated a reply. I'm driving. I'm not looking at my phone, you know. And then it read it back to me to make sure that it had it right. And then we had a little text message exchange, Ron and I did. Sometimes I had to tell the phone, nope, you got it wrong. Try it again, you know. And then I got to the clinic. I rolled the window down. Oh, it had told me that the clinic was closed, by the way, and that was because the clinic was closed, but they were having this clinic they were having the shots in the parking lot. So I just drove through, rolled my window down, stuck out my arm, got my shot, rolled the window back up, and asked my phone to give me a list of coffee shops near me, because this is a different town. And so it gave me recommendations, it told me the hours, it just picked ones that were open, and I picked one and got driving directions from Google and went there, had coffee. I was gonna work on slides for this presentation, and their access point was down, their internet was down. So I used my phone as an access point, right? And worked on my slides, and then I finished up and I got in my car and I got driving directions to go home, and I said, call my sister Jo, and it said Joe Mobile or Joe Work, and I said Joe Mobile, and my sister was in Hawaii on vacation. That's 4 time zones away from me, and I looked it up on the map, on Google Maps, and it's roughly the same distance as Bucharest to Nepal. So I'm making a phone call, hands-free, to my sister, waking her up, because it's early in the morning there, and it's this incredible distance. And Colorado is very mountainous where I live, and so I was even driving on a road that didn't used to have connectivity. You know, you just couldn't get access. Maybe there are places in Romania that are like that. And I got home and I thought about it, and a decade ago I was making Android phones. I was working for a company called Aircell at the time, since it's become Go-Go Business Aviation. And we made our own Android phones. And none of the stuff that I did was anything that I could have imagined a decade before. I couldn't imagine that voice to text could be that good. I couldn't imagine that coverage would be pretty much universal. I couldn't imagine that it would, it could read the maps, or it could read my calendar and tell me what was open and what wasn't open. And if that's a decade, 30 years is like insane, so I can't predict what's going to happen in 10 years, but I can predict what kinds of things might reappear. I probably can't guess what the guise is. However, all of that stuff, every bit of it, is internet-based. And so talking about internet applications and services without talking about the internet itself, is like talking about fish and never mentioning that they live in water, right? And so it's these guys, you know, it's Anisp, it's ESOC, that you need to support if you're going to actually take seriously the idea of using internet application services, of watching to see what's going to happen in internet applications and services, you need to go thank those people. And so who here is actually from ANISP or ISOC? Anybody? Somebody, right? So go thank those people when you get a chance. And pretty much I think that's all I have.
So now I will speak in English for them. I realized an interview with Esther Dyson on 8th of September this year. It was more than 30 minutes, so I will project here only 15 minutes. But it was very interesting. Esther Dyson was the lady who was behind the new infrastructures development in America when Al Gore was the vice president. She worked in the National Advisory Council. She was founder and the first director of the second, because posted, of the ECAN. And she is an investor, always she was an investor. She's a journalist at the basis. And I will present you some part of this interview which is referring to social networks and what's happening today. I want to ask you, because this conference is organized by some ISPs, by the Association of Romanian ISPs, and also from ISOC Romania, which is a user part, Internet Society Romania. What is your perception about companies providing today the internet services, like ISPs, content delivery networks, and exchanges? To include also here the GSM and everything which makes possible the portability of internet of things, and all telemedicine, teleworking. What is your perception about?
My perception of them is, honestly, now the interest is much more towards a higher level. The interest now is towards a much higher layer, the content, the social networks.
Sure.
All the applications and content that moves across them. It's, it needs to work, but the actual connectivity is considered more of a commodity, fast or slow.
But it's very important.
It is very important, but people...
Nobody sees it, but it's very important. It's on the basis of everything.
Well, it's like the water supply, it's like the train system, it's fundamental, but it's not, it's a different business.
Okay. But I want to tell you something. Let's refer a little bit to the social networks.
Okay.
Facebook and this. I have 2,000 plugs for students in a place. Our company maintains this. And sometimes chatting on Facebook, they don't realize that the internet is not working, or the plug, the electricity is not working. And I have some scripts in their chat room to tell me what is the issue. And then they send me a SMS on an old telephone. Say, go and send the supervisor to start the power at the floor number 7. This is not bad, because they don't realize where they are and how it's working. People from the social network, young people.
Yeah. I mean, this is the way the world works. People make things accessible, and then, quote, normal people don't really understand how they work. They don't know about plugging things in. They don't know about, the reality is also they don't know about the security that keeps them secure, or that does not keep them secure. They become susceptible to security breaches, to misinformation, to all kinds of stuff. And so, in a sense, in a world of social networks, in a world of misinformation, it's important to be much more aware of those kinds of breaches than of just the physical ones, and to reduce your vulnerability, not so much with VPNs, but kind of with common sense that says, does this make sense? Should I believe it? who's sending it to me. And in a sense, you need to be aware both of your own motivations so that you're not manipulated by social network, whether it's politically or to spend money you can't afford.
Huge discussions about this, yeah.
Yeah. And you also need to understand not just your own metabolism and how you get seduced, but you need to understand how these companies are focused on making money rather than delivering good content. Or, yeah, it's important to understand much less, quote, the motivations of AI, but the motivations of the people now using the AI to try and manipulate the people using all these amazing things that the internet brings to us.
What is your opinion about property on internet? Because in the past you were proprietary of your own data. Now it's not exactly the same because you have to use one of the 5 big platforms.
I think the notion of owning data is...
I refer here to Steve Berners-Lee project with a Solid, for example. Solid project.
I guess what I'm trying to say is something more different and more fundamental. You can't really own data. Once it's out, it's out. But what you've got is the ability to control it. I mean, NFTs in many ways have been sort of a failure, but the notion of a contract that's not I own or I don't own, but I have these rights, I assign these other rights, an NFT that would be updated with provenance information. It's more about the transparency in the contracts, which are complicated, than the simple notion of owning, because there can be 5 pieces of data which in themselves mean nothing, but when you put them together, suddenly they mean something. And so it's much more complicated than binary, I own it or I don't own it, because I perhaps delegate certain rights, control other rights, and we need better, it's like supply chain transparency, we need that around data.
What is your feeling about business generated by social networks, and how involved are you involved still in this?
How am I involved?
I like investor, of course. In this today.
Yeah.
In
So
the I know.
I have some investments in various of these things. I had a fair amount of Facebook that I sold a few years ago near the top, I'm happy to say, or actually donated to my Wellville project, which is my full-time job right now. But I think most social networks have become, put it this way, they started out with very nice DNA, but they started out with very nice DNA, but their metabolism overtook their DNA, and so they're now run by this insatiable need for more money. So they manipulate their users in a way that makes the users regret using them. And that's what a bad decision is. It's not one that turned out badly, but it's one that you knew you shouldn't make, but you made it anyway, and it turned out badly.
Yeah, but this cannot be reversed easily.
No, but that still doesn't mean I can say it.
Yeah, things are going forward, not backward. Yeah. And
so the solution to that is much more educating people to be less vulnerable to these social networks, to have, strong self-awareness, to be secure and not susceptible to being addicted, whether it's to social networks or to drugs or, power, whatever. And these algorithms that the companies use, whether they're quote AI or just statistics, are very clever at discovering people's vulnerabilities and manipulating them and making money from their data, charging them for things they don't really want, sending them places they don't really want to go. It's something we need to, like a pandemic, we need to develop immunity to it rather than think we can eliminate it.
What about these new trends with OpenAI and ChatGPT and the usage of this, because my guys are using intensely this.
Yeah,
To write some pieces of code and then to complete and to correct, and that's all. And
it's great stuff. And even as we use more AI, we need to train people how to use it, but we also need to train people to be better humans, not better users of computers. And that's, that starts in childhood. It starts with good parents. It starts with, again, this self-awareness of what is it that makes me human? What am I vulnerable to? How can I make myself more likely to do what I want to do rather than be distracted by all this computer stuff around me?
Yeah, when I talk with young students and this, I explain them that artificial intelligence was in the 80s on the PDPs we are using, but now the data is larger and the speed and the quantity of data. So that's the main issue, and this is possible only through the internet.
Yeah, I mean, AI is, in a sense, it's what we don't quite understand yet, and it used to be just simple logic and statistics, and now it's much more emergent capabilities. That one thing, so people live at a rate. The movie Her is one of the most wonderful movies because it's a man and an AI, and the man falls in love with the AI, and the AI has, I think, 1,500 lovers, and because she operates at a pace so far beyond the pace of the man, it's about a mismatch of timescales. And he's much richer, he's a human, he's emotional, he's sentient, and she can just do a lot more in less time, but there's the biggest gulf between them is that timescale. And you're right, I mean, the AIs do stuff at tremendous speed, but they still, and at some point, it's not that I don't think an electronic thing can somehow transform itself, but that's still going to take a while. We are still chemistry and biology, and we're just much slower, and at the same time much deeper.
Yeah. We have to stop here because of the schedule. The interview is 36 or 40 minutes. I'll put on the web and you can watch it later completely. It's about founding of ICANN and some other opinions. Now I want to go to another topic. In the 80s, when we had no Ethernet boards here, except one of my friends who will talk, there was it was an internet in the United States called NSFNet, were developed by Van Cerf, and it was with IBM computers running a strange operating system called BSD. Because this started sometimes in 1983, it was the first TCP/IP stack and the first operating system who worked on the large scale was compared to that time on the internet. So it was the big push to develop the internet, and we have now the chance to have here with us Mike Karels, who took the place of Bill Joy in the California Computer Development Group at Berkeley, and he was the chief of this project, the head of this project for years. BSD, BSDI, and FreeBSD. Mike?
Good afternoon. Unlike the other people in this session, I'm talking about something fairly long ago. In fact, about 40 years ago. So the topic is BSD's role in the early internet. So first of all, what is BSD? BSD stands for Berkeley Software Distribution. It's a series of software releases that were distributed by the University of California at Berkeley. The releases started unnumbered. It wasn't planned to be a series. There was the Pascal tape. There were various other add-ons for Unix, like the C shell and VI. And that gradually grew into something a little bit different, which was eventually called the Second Berkeley Software Distribution, or 2BSD. Thank you. 2BSD started, again, as PDP-11 add-ons. So this was version 6 Unix on a 16-bit mini computer. And it started out with the add-ons, but eventually it went to full systems. So it had modified terminal driver, for example, various other things in it. And I'll talk very briefly about one of those in a minute. About that time, the VAX came out, a 32-bit mini computer, and it supported virtual memory, unlike the PDP-11. So Unix got ported to that by Bell Labs, but it didn't support virtual memory, so Berkeley did that, and that came out as 3BSD, and then other things came out as 4BSD, 4.1 BSD, et cetera. So these were developed and supported by the CSRG, the Computer Systems Research Group, at the University of California. And so the systems became known as Berkeley Unix. So I'm going to talk a little bit more detail about 4.2 BSD, which came out in September of 1983, so just about 40 years ago. It had the first widely available TCP/IP implementation in it. It wasn't the first TCP implementation, but it was first widely available. It was done on a version done at BBN under contract to DARPA, which was the Defense Advanced Research Projects Agency, if I recall correctly. And that was a contractor in the government that contracted for advanced research. It was then integrated and enhanced by Berkeley to the point that when Berkeley got the final version from BBN, Berkeley said, no thanks, we like our version better. It also included the socket interface to networking, which was designed to be a protocol agnostic interface. So when you constructed an address to hand to a TCP socket, you didn't just give it an internet address, you gave it a sockadder structure, which has an address type, internet, and it has a 32-bit, happens to have a 32-bit IP address, 16-bit port number. It also included user-level networking support, support routines like, say, get host by name, which would translate from a host name into a network address. And that was done at that time by just a table lookup. There was a big text file and later a hashed text file, but it had complete addressing for the internet, such as it was. It came with a number of utilities, some of them, a number of networking utilities. Some of them were the so-called R commands, rlogin, rsh, rcmd, rcp, and it also included the standard protocols like telnet and FTP. Ran on a VAX again, and like the other releases up to this point, it required a Unix source code license. That really didn't matter too much because the target audience already ran Unix, which for these systems required a Unix license. That became more of a factor later. So a little bit about my involvement with BSD, how I fit into this picture. I started out as a graduate student in molecular biology, took a left turn at some point, started hacking on things on the PDP-11 in the lab, ended up being one of the authors of 2.9 BSD, which was a complete 16-bit PDP-11 Unix system. And then I went from there to being the principal programmer at CSRG, which was a big promotion. And that was in July of '83. And you'll remember that 4.2 came out in September of that year. Obviously 4.2 was mostly done when I started. Bill Joy and Sam Leffler were the two people who had done most of the work, including the design and refining the TCP/IP engine, doing the socket interface, et cetera. So suddenly I was the developer and maintainer of the most common TCP/IP implementation on the internet. So talking about BSG and internet development, 4.2 had a test release called 4.1c, but it wasn't very widely distributed. It was used in universities that tested this. 4.2 was much more widely used at universities and also research organizations. Was used on the ARPANET, which is the ARPA research network funded by DoD in the US. Later the MILNET, when that was split off from the ARPANET. Was also used on local ether networks because Unix didn't previously have much in the way of networking. And then of course there are some things that routed between the two, so it was a true internet at that time. 4.2 was also the basis for various commercial systems. Sun Microsystems, as mentioned earlier, Digital Ultrix were derivatives of 4.2 BSD, and various parts of 4.2 were used in other commercial versions. Now at this time, this was the first release to support TCP/IP on a wide-scale network on Unix. And so, needless to say, there were a few bugs, and it didn't have very sophisticated algorithms. It had the algorithms that you needed to open, close a connection, et cetera. But it didn't have things to deal with some of the problems that started creeping up. So it needed bug fixes, and it needed new and additional algorithms. So I'll talk about the Nagel algorithm. This was the first algorithm I added to 4.2 other than bug fixes and things like that. There was this guy, John Nagel, who had a rather tortuous path to the internet. It'll sound sort of familiar. He had a 4800 baud connection, which in turn, that went halfway across the US, went to a 9600 baud connection the second half of the way across the US, and then connected to MILNET. And so, needless to say, there were problems with this path. And John looked at the path and what was TCP doing, and there were a lot of cases where there were multiple packets for the same connection in the same queue. And so he had a nice self-tuning algorithm to gather up packets during one round-trip time. And if the connection was fast, like a local area network, you type a key, you'd get an echo, connection was idle again, no more delay. But on a slow link like the ARPANET, it would delay things up through a round-trip time. So I looked at implementing this, and I found the right place in TCP output. And there was a 3-line test that was somewhat complicated, and I looked at it. I thought, if I just delete the middle line out of those 3, then I'll have the Nagel algorithm. So I deleted that line, and I tested it, and sure enough, it was the Nagel algorithm. And so, needless to say, I went looking for another line of code to delete, make things better, but second one wasn't quite so easy. So a couple of years later, it's formatted differently in PowerPoint, but I think you can read it. A couple of years later, the ARPANET was becoming heavily overloaded with the number of systems that were becoming attached to it, and it was the main long-haul network for the US. So it used 56K links, which were not bad when it was first started, but it was getting to be a bit slow. It used packet switching on mini computers called IMPs, or interface message processors. Round-trip times were getting to be fairly long, up to about 45 seconds or even more. So typical connections would retransmit frequently. And it turned out most people would just say, well, again, there's not enough bandwidth. What can we do? But this guy named Van Jacobson worked up the hill from me at Lawrence Berkeley Lab, looked at it, and like John Nagel, he saw there were a lot of retransmissions. And so he looked at the code and he looked at the behavior, and the two didn't match up. The code said, just send when the window allows it. But the behavior would send out batches of packets, say like 8 packets at a time, and that would be a window of packets, and that would overflow the queue at the next hop router to the bandwidth limited network. So he called that blast and lose, where you'd send a window of packets. Some of them would get dropped, stop, retransmit, fill in a hole or two, and then sent another whole window of packets to catch up, and of course it would happen all over again. So Van invented an algorithm which had a cute name called slow start. And obviously what you want to do is, instead of starting out very quickly, you want to start out slowly. So it would open the window by 1 packet per packet, which is an exponential opening. You start out the connection with just 1 packet, the SYN, and then when you got back the ACK for that, then you're allowed to send 2 packets. When you get back the ACK to the second of those, you can send 2 and 3, and then the next packet you can send 4 and 5, et cetera. So this was a good algorithm to try to tune the hosts to the network. This was good to a point, but if your window is still too large, you would still overrun the network. And the reason for that is that if your total window would overflow the buffers on the routers, then you would still have problems. So there was a congestion avoidance algorithm that Van invented, went along with slow start. So once you got to about where the last drop packet happened, window of a certain size, then you would start opening the window linearly, probe for additional bandwidth, but not open it quite so quickly. So this went fairly quickly from being an experimental algorithm that was being tested at Berkeley to something that Berkeley's test sites, various universities got updates from us periodically, and they used it, and it helped a lot, and it made things better for the hosts that were using it. So it actually went from an experimental algorithm to a required algorithm in just a couple of years. It was published in SIGCOMM 88, if you want to look at it more. Later, there was an algorithm added called fast retransmit, which recovers from lost packets more quickly. If you had a couple of lost packets in a window, you'd stop, retransmit the first one, retransmit the second one, eventually get started, but you lost several round-trip times worth of data sending ability. And fast transmit, you lose less than 1 round-trip time. So it seems like it works faster than the speed of light, but it doesn't. So there are other BSD influences on the internet. One of them is involved with the domain name system. So I mentioned that there was this big flat table of internet addresses, hosts and internet addresses, and that obviously didn't scale very well. As a matter of fact, at its peak, I believe there were 6 people maintaining that table full-time. So Paul Makapetris, not at Berkeley, designed the domain name system, or DNS, and he did the first implementation on TOPS 20. Second implementation that I know of was done at Berkeley by a group of grad students originally. And they called it BIND, for Berkeley Internet Name Domain System. And it was integrated into BSD. The server called named was one of the standard services. The C library resolver replaced get host by name, so old programs would still work. And this was probably the most widely used DNS implementation for quite a few years. And so that had quite a bit of influence on how things got done, including how hostname lookup got done on BSD-like system, or Unix-like systems. Berkeley also influenced internet standards. There was a group called the Internet Engineering Task Force, IETF. Host requirements RFCs were done there. And I spent a lot of time at committee meetings there. Eventually there were a couple of RFCs, RFC 1122, RFC 1123, which are internet host requirements RFCs. And so Berkeley had a fair amount of influence on that. I mentioned also the socket interface. There was a group called POSIX that was doing Unix APIs, which is where I met Jeff, actually. But they decided to standardize network standards, decided to standardize 2 standards, including the socket standard. So I had a lot of input into that. So that was another big influence of Berkeley. I want to talk a little bit about BSD and open source. All of the things I've talked about so far were in 4.2 and 4.3 BSD, licensed Unix systems. We had to have a Unix source code license. Now, CSRG received a number of requests for partial releases, just the TCP code, just the telnet code, whatever. But we had no mechanism for doing partial releases, no way of delivering it, no way of licensing it. And in fact, we hadn't verified that any particular part didn't have Unix source code in it. So there was a new release called Net1 that we put together. We reviewed the code. It was a vertical slice through the system. It had user level code, clients and servers. It had library code. It had kernel code, the TCP IP protocol implementations, the socket layer. This was made available with the new BSD license and a new BSD copyright, which says you can basically do with what you want with it as long as you give us credit and don't sue us. And then there was a version called Net2, which included a nearly complete system, had a few missing kernel files, but there was a little lawsuit that intervened. And after that, there were new releases from Berkeley. 4.4 BSD Lite was the first release after the lawsuit. And that included everything that was in Net2, some minor exceptions, and was open source, was Berkeley licensed. I'm going to do this one very quickly. There was a company called BSDI that was developed a version of Net2, which was a complete system and sold it commercially. Unfortunately, when they advertised it, they used the phone number spelled out as 1-800-ITS-UNIX, which may have been the trigger for the lawsuit in question. In any case, that was filed by USL, which held the Unix trademark and patents, against BSDI, and then later against UC Berkeley as well. So the lawsuit was settled. BSDI first release 1.0 came out. There had been a number of test releases sold before that. And this was used in a number of commercial firewalls, routers, was used in websites later. And believe it or not, I believe BSDI was the first commercial site on the World Wide Web. I can't verify that. I guess I'll say a few words. It was founded by some BSD developers, people related to Berkeley, including me. And so it was kind of people who already knew this code who developed the new system. One other thing I wanted to mention is that although the BSD sort releases from Berkeley ended a while back with 4.4 Lite, there are a number of BSD systems ongoing. There are the main three, which are FreeBSD, NetBSD, and OpenBSD, which started based on Net2 and or 4.4 Lite 2, or split off from the others. There's one called Dragonfly BSD. There's another one called Darwin, which may be less known. But Darwin was done by Apple, and it was the base for Mac OS. It was open sourced. I'm sure by now Mac OS has diverged tremendously from the original BSD code. That was another influence of BSD on the network. So at this point, I'll take any questions. Yes?
Yeah, I'm wondering,
Oh, wait for the microphone.
thank you very much. Sorry. Yes, okay. I'm wondering, you mentioned some legal lawsuits, but didn't talk about this. You had everything to succeed. I mean, I look at the code, I'm a BSD user, one of the last ones, instead of Linux. But I'm feeling like I'm becoming lonely, because even through NAS, as an example, switch from FreeBSD to Linux lately. How was the influence of this lawsuit in the development of BSD? Because you didn't mention this.
That's hard to know.
Why did you lose this war? Because the code is brilliant compared to Linux. Linux is a mess. It's still a mess. Even Linus Torvald recognized this as a kernel founder. Instead, BSD is done by engineers, and I don't get it. I mean, it's an anomaly why you lose the market shares. And now in BSD, I cannot, it's not my main system, it's an Apple one based on BSD, but in drivers, for instance, you don't have companies involved in developing the drivers. This is why Linux is gaining momentum. Thank you very much.
Well, Linux has more market share. There's no doubt about that. There are a lot of BSD users. I'm part of the FreeBSD community, and it's very active. There are fewer drivers for FreeBSD, but we've been fairly successful in getting companies to dual license their drivers, do a BSD licensed version as well as a GPL version. There are people, including myself, that think BSD is more structured. Maybe it's the engineering background that you mentioned. I'm not sure. I myself was trained in molecular biology, so that didn't help much directly. But I think it's a matter of opinion. That some people think BSD is a cleaner system, more maintainable. So, but it is really a matter of personal taste at this point. Is there another question?
How do you think, Mike, being trained as a biologist instead of being trained as an engineer has affected the way that you do software?
I'm not sure how to answer that, to tell you the truth. I'll have to think about that. Any other questions? If not, we're probably getting close to our time limit. So. Okay, thank you.
Thank you.
Paul Vixie is one of the history. Let's say he's one of the Internet Hall of Fame's nominees. 2014, he developed the DNS. He developed secure DNS and many other things like maps. Like now he's a vice president for security at Amazon IFVS. And I'm very glad that we can have him here in this conference, because this is a conference exactly suited on what he develops. Okay, your turn. Yeah.
I certainly glad to be with you. I wish I could be there in person. I've had extensive business travel for work, and so it was simply not possible for me to get to be where you are. So again, I thank you for this invitation. I wish I could be there in person.
You are welcome.
Perhaps next year. I want to talk today about some changes which are coming to the internet, and they are somewhat inevitable because the team who works on these things are volunteers. And it is the consensus among those volunteers as to how they move forward. And we were not there. And that means that the outcome that we're going to get will not necessarily be best for security and resiliency of the internet itself. So I'll speak first about the nature of modern site security. By site, I really mean a edge network that connects to the internet, but it also has some local devices. So this might be a family's home or a corporate network belonging to some commercial entity or perhaps government agency. The internet is a network of networks. We all create those networks and then connect them to the internet. So every edge network contributes some part of the total internet. And every edge network in this terminology is a site. It is a place where things happen. And the security of those sites has dwindled. It's really quite rare now to encounter an edge network, privately operated, secure edge network that is actually secure. And to the extent that it will be secure, it is heuristic security. We try to look at the actions, the packets of each host connected to our network, and then from those patterns, we discern whether that host is acting according to policy. And that's a very weak mechanism. But, if you don't have the source code, if you did not build the device yourself, there's no other way to know what a device is doing except to look at its packets. This is hard. It's just hard because you don't know if that IoT device or even your smartphone or your laptop is making the network traffic that you see. Maybe it's something you asked it to do. Maybe it's something that it does to phone home and to tell its maker what to do. But you don't know other than by looking at that traffic. And, so just looking at the traffic is a weak system. It's not what we would have chosen. It is, however, what little we have. I'm concerned about having less. It's important to remember the reasons why site security is so limited. Has to do with growth. When the complexity of your system increases, but your understanding of that system does not increase with it, then you're at a growing disadvantage. And it'll turn out from a internet security point of view that the attackers will understand your network better than you do. They'll understand the devices on your network better than you do. And by complexity, I'm not limiting it to hardware, although certainly hardware does get better every year. It's called Moore's Law, and we get more transistors per chip, more memory, maybe a faster cycle time. We get the same performance from something smaller. You have more lines of code, more programmers having participated in creating those lines of code. The code is in need to be patched, but increasingly it does not get patched. In many cases, the maker of the hardware will have gone out of business. There is no way to get a patch, even though there is a known vulnerability. That's the kind of thing I mean by the gradual increase in complexity. Yeah, and there is a philosophy which has come into its own here, where a corporate network assumes that a breach has occurred. They assume, in other words, that on their network right now, there are devices which have been taken over. The control of some of their devices is in the hands of bad actors. We would call this a botnet, and they are so prevalent that many sites assume that there's a botnet, maybe more than one botnet, operating from within their network. This sounds terrible, but it is realistic. This sort of thing would lead you to no longer trust the devices closest to you on your own network, and to make sure that they're not in a position to eavesdrop. This is terrible, but it's all we have. And let me remind everyone that in this type of a Cold War between those of us who defend and those of them who attack, the advantage always lies with the attacker. They can study our defenses at their leisure. And when they win, they profit. Now, we do not have the leisure of studying our devices. In other words, we're here to do something else. We want to use the network to do something important. And so the study of the network is not our primary goal. We don't work on it all the time. And when we win, we do not profit. Our benefit if we win is that we do not lose. But we don't know, had we lost, how much we would lose. The attacker knows if they win, how much they won. So there's a structural deficiency in the way we've built the internet that has led us to this position where we are at a perpetual disadvantage. So we're in a point in time, and that point in time had some road marks. Specifically in 2013, a large change was input. And what happened was a government contractor, a single person, had some kind of a crisis of faith and put a great many US government files onto a thumb drive or a series of thumb drives and walked out of the secure government facility with those thumb drives and then flew to Hong Kong, where he disclosed the contents. And it was a big event. This was the biggest headline in our field that year. And in fact, many of the things which he was able to disclose were quite disturbing to many in terms of the common practices of the National Security Agency in terms of eavesdropping on its citizens or committing various, espionage actions against non-hostile parties. A lot of people in the world were shocked by this, because if you don't know how history has progressed, you don't know how we got here, you don't know how the world works. If you're suddenly told this is how the world works, it can seem like quite a shock. But, for me, at least, I assumed that something like this was going on, because that's what governments do. The people who are doing it are patriots trying to defend national security for, in this case, the United States of America, but also for all of the allies, all of the friendly nations, all of the trading relationships around the world were also part of that which was to be protected. And it's certainly it's hard to hear how this is done. It feels like dirty tricks, but this is how nations operate. In the history of the world, nations that don't operate this way don't last long. Anyway, those who were panicked went to the Internet Engineering Task Force and said, we can't live this way. This is a terrible thing, and we must use the internet to change it. And so one of the immediate outcomes was RFC 7258. The RFC series is like a Bible for internet engineers. It's telling you what to build and how to build it. And in this case, what they were told was encrypt everything. Assume breach. Do not transmit clear text signal, because it will be seen by nation state actors and potentially also commercial actors who do not necessarily have your company's safety as their first concern. Title of the document was Pervasive Monitoring is an Attack. And, we must give credit to the truth. That is the truth. it is a uncomfortable truth that we live with. Some years later, they added to their Bible another RFC 8890, wherein they decided that the internet is for end users, because it seemed that it had become unclear why do we build this thing and who are the beneficiaries? Do we build it for the nation state security apparatus? No, we don't. We build this for ourselves. There are some naive problems with this model. And I say naive because the writers of these RFC documents are absolutely passionate about personal freedom and autonomy. They are on the side of humanity itself. They are trying to undo the state of affairs which Edward Snowden showed to them. They are trying to get us to a place where end users are the prime movers of the internet. So an example of the naivete of these passionate defenders of freedom is that there was no carve-out, no exception made for site security. And in the case of site security, you must be able to do pervasive monitoring. You must know what the devices on your secure private edge network are doing. You have to be able to look at the traffic. And that's not a good security model. It's just all we have left because we don't have the source code to all those devices, as we might have in the pre-commercial era of the internet. And they made no distinction about what kind of end users they meant. So it's not clear if they mean that the internet is also for intruders or malicious insiders or botnet operators or the poisoners of supply chains. There are a lot of end users who might wish to use my network, and therefore it's to their benefit that we say that the internet is for them. But it isn't. I build my own corporate network. I build my own home network. It is not for the end users. It is for me, the builder. And part of my job is to protect the end users against poisoned supply chains. And so if you build a network that I, as an edge network operator, or any of you as edge network operators, have no visibility into, you may have made the situation worse for the population you're trying to protect. They also made no distinction for surveillance capitalism. In other words, some parts of your supply chain, your smartphone, your laptop, whatever, might be in the service of its maker more so than in the service of you. And so you might need to be able to see the traffic so that you can audit the security assurances that were made to you by your smartphone, or the maker of your smartphone, or the maker of your laptop, the maker of your set-top box if you watch TV. So this was done, and it was done in ignorance of other facts, and that's going to have some impact. So if you're going to defend this stuff, you're going to be breaking some rules. There are rules in the Internet Protocol Suite that specify, for example, that data transfer is end-to-end, and that middle boxes shall not tamper. We break that rule every time we install a firewall. And it's necessary to break that rule, right? So that rule is itself somewhat naive. If the internet is still a network of networks rather than a network of end users, including intruders, then we're going to break whatever rules it takes to fulfill our security mandate toward our family, toward our customers, toward our employees. And you know, what's happening when you encrypt everything is that very necessary thing becomes harder, if not impossible. So let me mention in passing the first protocol which implemented these new philosophies was described in RFC 8484, which is about doing DNS over the HTTPS protocol. HTTPS is the web protocol. It is the thing that our web browsers use to fetch almost all of the content that we see. It is a ubiquitous, universal protocol. It's used for almost everything. And it was chosen as the bearer for DNS because of its ubiquity. And that's because DNS is a very frequent target for surveillance. If you can see DNS, then that will help you to characterize the rest of the encrypted traffic that follows DNS. So it's a really interesting target for attackers, whether they be intruders, surveillance capitalists, or nation states. Everybody wants to know what the DNS signal contains. And so on the first page of that RFC, they say that a use case for this protocol, the reason it exists, is to prevent on-path devices from interfering in DNS operations. Okay, that's very clear. What's not clear is that my firewall is on-path. It is an on-path device. And I intend to interfere because it's my network, it's my devices, it's my family or my employees. So I have both a right and a responsibility to do that which this protocol intends to prohibit. Later, RFC 9000 and a series about maybe half dozen RFC documents, they've advanced beyond DNS over HTTPS, and they pretty much want to replace the TCP/IP protocol, which is what we use for everything, including HTTPS, email over SMTP, secure shell over SSH. It all uses TCP. And so now they are replacing TCP with a more secure protocol that is secure by default, as opposed to TCP, which is clear text by default, and you have to decide that you're going to encrypt. With the quick protocol, you don't get to decide whether to encrypt. It only works when it's encrypted. And in terms of manageability, there's a document which claims that the quick wire image is not specifically designed to be distinguishable from other UDP traffic. UDP is the peer protocol of TCP. It is the user-defined payload or user-defined protocol, and it is much more lightweight than TCP. It's not reliable. You have to, explicitly acknowledge UDP, usually by answering a question. DNS traditionally works over UDP, NFS, NTP. All of these things work over UDP. If you've ever tried to boot up a router using the TFTP protocol, that was UDP. And so what they're saying here is that quick is kind of mixed in with your other UDP traffic. And it's actually not true, what's written here. I mean, it's true as far as it goes, but it's misleading because the quick wire image was specifically designed to be indistinguishable from other UDP traffic. And I argued that the document ought to say that, but I did not achieve consensus. In any case, this traffic will appear on your networks, has already appeared on your networks because early versions of it are already present in the Chrome browser. And they're already spoken by various web servers, including those at Google. So this is already happening, but it is not yet a universal recommendation that all devices speak this protocol. That recommendation is forthcoming. You should think about what this means. Now, this would not be as big a problem without a corresponding change being made to the TLS protocol. TLS is the Transport Layer Security. It is the security that we use on the web. This is ubiquitous. It is universal. And the version that we use now is version 1.2 of the TLS protocol. But TLS 1.3 has been standardized and will shortly be recommended. In TLS 1.3, there is a change to part of the signaling. In particular, the server name indicator, which in TLS 1.2 is in the clear, can be seen by a non-path actor, firewall, for example. In TLS 1.3, this information will not be in clear text, and it will be possible for TLS protocols to work perfectly well, but to not expose to your firewall what is the intended target, what is the web server name that we're trying to reach here. And so those of us with so-called next generation firewalls can no longer have a policy of permitting the visitation of some websites by our family or our customers and forbidding others. That policy becomes unenforceable once the traffic becomes undetectable. This was a goal. This is not an accident. Our firewalls are seen as equivalent to the real problem, and thus no provisions have been made or can be made to let those firewalls have the visibility that they wish to deny to nation-state actors and ISPs. We are like a baby being thrown out with the bathwater. We don't have good choices. And if you're in a position where through no deliberate action of your own, you have no good choices, you feel that you must do something, but there is nothing that you can do which appeals to you, that usually means that you are in a fight, that somebody has chosen to have a fight with you. And one of the powers that they have, this happens in all combat, all conflict, is that your operating conditions will be changed by your attacker. And the alternatives that you have, the defenses, in other words, that you might employ, have also been managed for you by your attacker. So as our traffic goes dark and we can no longer see what our own networks are doing, then we're going to have to do something about this. Some sites, many, maybe most of the edge network will do nothing because they can't invest as necessary to try to keep control of their operating conditions. And so for those, they just have to learn what are the new rules, and especially what are the new incapacities. There may have been a time that a corporate network operator could be told by some outsider, hey, you're DDoSing me, you're spamming me, you're sending me traffic that I don't want, please stop. And it used to be that you could look at your edge network device and figure out, well, where is that traffic coming from? And you'll find that perhaps some electronic toaster in your kitchen has been taken over by bad people, and it's part of a botnet, and all you have to do is unplug the toaster and you can stop the attack. Well, now you can't. Now, if somebody complains to you that you're spamming them or DDoSing them or what have you, what you'll be able to do in this new world era is to say, I have no knowledge of what my network is doing. I cannot take responsibility for the emissions of my network. I feel sad that you're being DDoSed, but there's nothing I can do. That is the new world. Others will make changes. And if they can afford to make changes, they'll be expensive changes. Right? These are not things that, oh yeah, we should have done that anyway. No, these are things which will cost in other ways, but will prevent this change from occurring. So if this change is an existential risk to your family, to your company, to your government agency, to the, in other words, the operators and users of a secure private edge network, you might make a change that is going to be hard. If you install an application layer gateway, like a proxy, and then you insist that every device on your network please use that proxy when they want to exit the network, you know, that's not uncommon for proxy settings to be managed by the enterprise. It's impossible to get this done for a family. And I must note that there is no configuration by which IoT, you know, that electric toaster, for example, can be told it the proxy to use. They all assume that they have end-to-end rights. And so if you move to this model where you have a proxy that must be used, you will be limiting the kinds of devices that can use your network. That is going to be an expense. You could also do what I do, simply block UDP by default and only permit it if it's coming from known DNS servers. You know, so DNS needs UDP, but only your local DNS server needs to speak UDP through the firewall. So if you know where your DNS traffic will come from, you could simply deny all UDP, except that which you know to be DNS. This is not as expensive, although it means, as an example, that the Chromecast device from Google will no longer work because Google does not believe that it can trust your local name server. It always uses 8.8.8.8. And if you block UDP, you're gonna have to change from your Chromecast to some other set-top box device. Apple is a good choice. The Amazon Fire Stick is what I use. But you must be prepared to sort of evaluate the cost of this on a device-by-device basis. What's worst is we're going to see innovation by those who wish to bypass these new operating conditions, new inventions, new protocols, new heuristics, new private relays, new ways to restore the old visibility. This will be a war of one-upmanship. It will be an incremental increase in complexity for the purpose of determining who gets to make the rules about traffic. Now, there were alternatives, you know, and what we see around the world in all of human history is that a lot of actors begin with an attack, and then there's a fight for a while, and then after the fight has gone on, then negotiations occur, and you decide where will be the new border, what will be the new laws, you know, who must make restitution to whom, that kind of thing. But the reason that you start with a fight instead of just asking for negotiations is because you want the negotiation process to be in your favor. You want to first improve the operating conditions, improve the status quo, so that when you negotiate, you're negotiating from that new position. And that's what's happened here. Eventually, we're going to have to negotiate with our nation state actors and with our firewall operators, and perhaps with our ISPs. It's difficult to know the shape of the conference table where negotiations will take place, but negotiation will eventually take place. I believe it will take the form of a protocol by which devices can learn the policy. And if they're incapable of following that policy for whatever technical reason or monetary reason, then they can simply fail, or they can take a risk and try to use the network against the local policy. So I think we're going to see a policy protocol that will make it possible for an edge network operator to negotiate with their supply chain and negotiate, I guess, with botnet operators and intruders and everyone else. That's not where we started for the reasons I've given. It's going to take some years before the battle has been fought long enough and enough costs have been paid by all sides before we will begin to work on this protocol. I wish it were otherwise. So that's my talk. I want to note that if you are, like me, a fan of the original Star Trek television series from the 1960s, you might remember an episode of that TV series where a new computer is installed, which turns out to be intelligent, and it wants to sort of take control and make sure that it cannot be interfered with. And so what's shown here is a still frame where the computer has established a direct power conduit to the ship's engines. It is an endpoint, and it has demands. And our endpoints on our networks are also about to tell us their demands. They're about to directly connect to the power core of the internet itself and dare us to unplug them. It's a bad state of affairs, and it's going to be expensive. And I thank you for listening to my story, and I hope we have questions.
Thank you. Thank you. Iberiu.
Thank you for the presentation. I would like to ask you what can be done with all the attacks, security attacks that come from Amazon Web Services and other type of services of the sorts?
Well, first, let me make clear that although I work for AWS, Amazon Web Services, I am on the security team there. I am not here today representing Amazon in any form. I am here as an invited expert on this topic. And I've been speaking on this topic for some years now, longer than I've been at Amazon. So I have some knowledge of how cloud operators prevent bad traffic from leaving their network. It's really no different from what I've said. All the cloud operator is going to have access to is the traffic flows. And most cloud operators are known to encrypt customer traffic. In other words, cloud users, companies who have put resources into the cloud. The cloud operator is, generally speaking, encrypting everything. And so there's no way to do payload inspection. All you can really do is look at the quality of the flow of traffic. And so, it may be that a DDoS looks like a DDoS, and you can see it in NetFlow, for example. And there are other bad traffic types which are similar. Inevitably, if a cloud is global and has a million or millions of customers, some of those customers are going to get breached. There will be malicious insiders inside the cloud, and they will do things that perhaps the cloud has a way to automatically detect and thus filter out. But maybe it's an evasive attack. It's designed to prevent detection, in which case the cloud operator would receive a complaint from some outsider. Hey, how come you're DDoSing me, or how come you're spamming me, or what have you? And in that case, every cloud will have a team. It's usually called the trust and safety team, whose job is to receive those complaints from outsiders and to investigate them internally to find out what is the cause, and if it isn't a customer infected with a botnet, to then work with that customer to improve the trust and safety of the whole network and of that cloud. So I hope you understand why I have to speak in generalities. I will not represent Amazon in this event.
Do we have news from Ed Snowden that you mentioned?
I have not followed Mr. Snowden's endeavors very much, but to the extent that it becomes news, I can tell you that he has spoken on the plenary stage, giving a keynote of sorts to the Internet Engineering Task Force. Now, of course, he could not do this in person because he is he's being sought. There's an arrest warrant for him, and their extradition has been requested. So if he leaves the country where he resides, which is Russia, he would be arrested and brought to the United States for trial. So he did not travel to IETF, but he had a kind of a robot. It looks like a little bit like a rideable two-wheeled robot, but instead of a person, it has a video screen. And so he attended IETF virtually in that way, and he spoke to the assembled audience in that way. But that's the only thing I have seen or heard in recent years. So as far as I know, he lives in Moscow. Presumably he's found work, and presumably is making a life for himself there.
My name is Otto. First of all, it's an honor, sir, to meet you even by conference. And thank you, Mr. Rotaro, for inviting me here. So I would appeal to your expertise in security. And maybe if you look ahead and can point us, how do you see, because we have this trend of migrating everything to the cloud, like all businesses, family photos, and everything. Mobile phones accelerate this. Do you see this trend returning? Do you see from a security standpoint, or will there be a reverse of this, maybe going to the edge again? How do you see the future here?
It's necessary that my perspective be informed by my experiences. And about 1.5 years ago, I was invited to join the security team of a global cloud operator. And some of the way I will answer your question has been informed by that experience. The idea of a so-called home lab, where somebody gets together a bunch of Raspberry Pis or other cheap systems that are programmable, and they install Linux on them, and then they'll create their own postfix server, their own Nginx server, and they'll play with this stuff so that they can familiarize themselves with how it works, or maybe even begin to explore new features by deploying them locally to find out if they work. That's how the internet was originally made, and there are still a lot of people who work that way. So I myself have always operated my own name servers and my own mail servers and so forth. And so I have a tiny little island of capacity, and that's what my family depends on for my family's operations. I did the same at my last startup company, Farsight Security. We did use one of the public clouds, but we only used it for encrypted backups because everything else we wanted everything else to be native. The problem with this model is that it calls for a type of expertise that is no longer universal. In fact, it's not even common. And that expertise is the ability to rack up a bunch of one-use servers and install operating systems and services on them, connect the whole thing to the internet, and offer your services to the extent that maybe you're in the business of providing services over the internet. That won't work. It won't scale. What you need to be doing is to have that capability across different regions. It cannot be that, for example, your service is very fast for those in Romania, but very slow for those in Hong Kong, as an example, as a random example. You're going to need some way to act globally. And the expertise required to replicate your services across the world and to make them available to user populations that are far from you is dwindling. The number of people who know how to do it is not changing. We're not creating new ones. We have an existing population which is barely replacing itself with death and birth. And yet the need to behave this way is growing. So the cloud was inevitable in that sense. And for a company, let's say, who is in business to do something, they may not be in the business of running their own web server. They simply have to have a web server so that they can do their real business. And I don't know what the real business might be. But for them, it would be very expensive to maintain a global infrastructure that they owned and then operate it and monitor it for capacity, for attacks, for the need to patch, the need to upgrade, the need to add capacity. These are things which would be costs for most companies, and there would be no corresponding benefit from that cost. In other words, becoming really good at that is not going to make you more profitable at the thing you're actually in business to do. And so it is inevitable that companies who understand their total cost of operations will eventually drift into or deliberately migrate into one or more public cloud. Now, some will pull back if it turns out that they actually have other reasons why they must be an expert at doing what the cloud itself will do. Then, yeah, you'll see them buying servers and putting them in data centers and internet exchange centers around the world and staffing for that. But that will never again be common because the need to do that is so rare. And so this becomes a build versus buy decision. And for most companies, it is much cheaper to buy it than to build it and to then own all of the problems. Now, since we're speaking mostly about security, I want to point out that every online service has a dependency on a stack. The service has to be somewhere, so there's dirt. And then there has to be inside of a building, so there's steel and concrete. That building has to have power and connectivity, and so there's electric cabling and fiber optic cabling. That power and that networking has to be diverse. So there's probably more than one source, and it has to be resilient. So there's probably a backup generator, maybe also an uninterrupted power supply. There's a router that connects the network to more than one upstream provider. There has to be servers, and those also must be resilient. So there has to be more than one server. So there's probably also got to be a load balancer. The server has to have an operating system, and then the services running there are software packages themselves. All of that has to be monitored to find out if there's a critical zero-day vulnerability, and we have to patch it right now, even though it's time to go home. So, and on top of that is the application, which might also have maintenance requirements. And then the customer data has to be stored somewhere, and that needs to be resilient. So you've got RAID, you've probably got multiple RAIDs with some kind of replication protocol. All of that must be done. And my question for anyone who is wondering about the total cost of operations of building versus buying is, are you going to be fully responsible for every level of that tree or of that stack, everything from the customer's data all the way down to the dirt? Are you going to be an expert? Are you committing in perpetuity to understanding all of that and to monitoring it carefully and to replacing it when depreciation occurs and it wears out, expanding it when capacity is needed, patching it whenever it needs to be patched, accepting complaints from outsiders in case you get breached and somebody's DDoSing you or copying your data to the dark web? Are you going to commit to full understanding of every single part of the stack between your customers and the dirt under the data center? I think no. I think you're going to have to count on others to do some part of that. Most of us count on the data center and the power and the cooling and so forth to be provided by someone else. And we count on the network to be provided by somebody else. And we don't necessarily create our load balancer using open source software. We're probably using an appliance for that, as we do for our routers and switches. From there, you have to make a similar total cost of ownership decision where the total cost of ownership includes securing everything. And if you're not going to commit to securing everything from the host and the operating system and the services and the microservices and so forth, then you have to find someone who can commit to that. And you have to bring them on board as a partner in your venture. That is why the cloud grows. Sorry for such a long answer.
It was perfect. Thank you.
So if there will be in time more questions, how we can reach you? I will collect them and send to you, or how we do? Because the time here in the room is limited and we cannot afford staying. Yeah. What do you think? They will send them to me and then I'll send to you and so such you connect with them?
I think that's fine. I would look forward to continuing this discussion with anyone in that room. I wish I were in that room so that we could talk in the hallways.
Yeah.
So let me just tell everybody, I'm on social media as Paul Vixie, one long 9-letter word, my first name, my last name. And if you wish to converse with me, one way to do so would be to connect with me on LinkedIn. If you do so, please mention this conference so I'll remember how we met. If you want to reach out directly, I am paulvixie@gmail.com.
Okay, that's good way to talk with you. Excellent. So again, thank you. I'm happy that we could do in this way. It worked. It worked better than 2 years ago when we met at that conference here in Bucharest. I mean, it will be more efficient for all the people in this room. So thank you again, and we were very happy to have you here in this conference. Bye.
I was honored by the invitation. I hope to be there in person maybe next year. Thank you all.
Okay, bye.
Urmează o prezentare înregistrată de o persoană care s-a distins atât în România cât și în Statele Unite ale Americii, Cloud of Clouds, care imediat va fi pusă on screen.
Deci este vorba despre colegul meu, Mihai Nelu, care a fost vreo 8 ani de zile directorul unui grup de dezvoltare la laboratoarele Bell Labs. A lucrat aici în România multă vreme, adică până în 92 am fost la lucrarea lui de doctorat și după aceea a plecat în Statele Unite. Și acum, după dezvoltarea sistemului de operare pentru rutere la AT&T în anii 90, atunci când a apărut și Java, a ajuns la un nou concept care l-a patentat de conectarea cloudurilor heterogene.
Hello everybody, my name is Nelu Mihai. I hope you are enjoying the conference and having fun. My presentation is a little bit more theoretical. It's about a project named Cloud of Clouds between one of my startups, Mosaicsoft, and Waterloo University, having the goal to create an infrastructure for controlling applications on cloud, multi-cloud, and what is more recently known as supercloud and meta-cloud, and helping the builders of these applications to have an easier life and to navigate this very complex environment using a methodology that is a little bit more structured. And it intends to create a theoretical model of cloud. A few words about the principles of this project. It is about yours truly, the presenter, and Professor Mahesh Punitara. Mahesh Punitara is a professor at Waterloo University. It's a long-time collaborator of mine. I am proud to say that I hired him when I was at Bell Labs and he was doing his PhD. Mahesh is a renowned expert in distributed systems, algorithms, security, networking, and of course, cloud. What can I say about myself? I'm an older guy, so I've been around the block. The project is funded mostly by my personal funding and with some contribution from the government of Ontario. It has a tremendous talented team, mostly PhDs, students and graduates, and it's intended to be an open architecture that addresses the problems in multi-cloud and meta-cloud. Well, this is probably the most important slide of this presentation. I'm trying to define the foundational principles of Cloud of Clouds. First of all, cloud is a programming paradigm which allows builders to design applications with data and logic inherently distributed. It's not a hospitality business. It's not about moving application from customer prem to hyperclouds. Secondly, execution units, data, and interconnectivity are equally important. Most of the cloud designs considered actually execution units and data are the essential part of the design, neglect interconnectivity, which is a mistake. We know for sure that different cloud technologies are heterogeneous, but having in mind this, we shouldn't abstract them using a common denominator approach, because this is going to limit their functionality. And if we talk about abstractions, they should be generated from a universal mathematical model, which I call theoretical model of cloud. All of us know that cloud is complex. Therefore, in this design, automation and optimization are essential for all the system. More important than open source is open architecture. Why? Because open architecture allows customers and third-party applications to be very easily integrated in this controlling infrastructure. Meta clouds is of course distributed, but it should be as easy to operate as one single computer. It should be logically centralized. And one axiom that actually I think is very important, and people don't give it enough attention, it's the following fact. Independently designed best-of-breed components assembled together or hacked together do not create a best-of-breed system. Now it's time to learn how Cloud of Clouds works. Let's suppose that I have a customer who runs their application on 3 clouds, Microsoft Azure, AWS, and Kubernetes on-prem. What Cloud of Clouds is going to do is interface with these accounts, start to process and discover all the objects that exist in them. And the result of this processing, it's going to be what we call a knowledge hypergraph. In fact, a knowledge base accumulating all the information that is needed in order to characterize these 3 accounts, but in one unified model. So practically every single object in those 3 clouds are described as nodes, edges, and their attributes in the knowledge hypergraph. Of course, the reason we want to have a multi-cloud is to run a workload on it. So let's go to the next steps of the understanding how Cloud of Clouds works. So we suppose that we have a complex workload that needs to be deployed on the multi-cloud using Cloud of Clouds. So Cloud of Clouds is going to use YAML files which describe the configuration and the instantiation of this workload, or a new YAML file can be written. But again, the result of the processing done by Cloud of Clouds is going to be another graph, which we call knowledge graph. So we'll transform this application configuration or workload configuration into yet another graph, which is going to be deployed on the knowledge hypergraph, which was presented on the prior slide. We mentioned on the slide related to the foundational principle of Cloud of Clouds that optimization, automation are the essence of the whole design. So let's examine a little bit how this whole mechanism works. We have on the left-hand side the knowledge graph, which represents the application. Then on the right-hand side, there is a knowledge hypergraph, which abstracts the infrastructure. Clearly, this knowledge graph is nothing else than a flavor of a neural network, providing the input into a deep learning system that can examine what's the current status of the Cloud of Clouds, try to figure out what are the patterns for the future behavior, and then using a prediction and inference mechanism to build a kind of control loop that changes the behavior of the system in such a way and remains on the same thresholds that the user is interested to work with. It's, if you want, trying to make an analogy, similar to the way that industrial systems are managed. So you have a system that evolves, and then you have a control loop that regulates the system based on the desire of the customers and keeps parameters in a certain thresholds. And this gives a very nice and elegant way of running for the whole life cycle of workload applications in meta cloud or super cloud. Well, we are at the last slide of our presentation, where we're trying to extract the essence of the design of Cloud of Clouds. So what we've achieved is to translate, if you want, all the objects and their related attributes from an infrastructure which is multi-cloud with heterogeneous hyperclouds connected to it. We transform it into this knowledge hypergraph, where every single object in the cloud is represented as a node, edge, and its attributes. We did the same thing also with the workloads. So in this way, we generated, if you want, a universal graph that is and represents the state of the meta cloud. In this knowledge system, we have, in fact, three models, sorry. One is a logic model, the other one is a connectivity model, and the knowledge model. So the logic model deals with execution units. The connectivity model deals with interconnectivity relationships, and the knowledge model is really about data and their attributes and how this data is supposed to be used. On top of this infrastructure, we build a set of services that are very useful in a meta cloud, such as security services, scheduler, optimizer, autoscaler, load balancer, an automation engine, and connectivity orchestrator. And by building this computational space, we succeeded to achieve a goal that is very interesting. We created a control infrastructure which doesn't hide the underlying hyperclouds. It keeps them relevant, but at the same time, it controls the behavior of all these applications in the meta cloud using a simple mathematical model that makes the life of application programmers or builders easier and it adds some structure to this heterogeneity of the hyperclouds.
Vă rog să vă ocupați locurile. Vom începe în curând. Avem o mică... un film și după. Prezint un... Da. Așa. Deci, recent, am discutat cu un coleg de-al meu care e plecat din 1992-93, se numește Mihai Nelu, datorită unei discuții care am avut-o cu Ion, am ajuns și am discutat cu el un pic și am zis, hai să facem un interviu. Eu cu el, care n-am mai vorbit de atâția ani. Eu am fost la teza lui de doctorat în 92, că atunci începusem să-mi pregătesc și eu teza. A fost foarte interesant. Și aici e partea a doua a discuției mele cu... Nu o să o punem pe toată, evident, o să rămână pe site să-l urmăriți tot interviu. El a reușit să comunice cu Tannenbaum în anii 80, 86. Tannenbaum i-a trimis Minix-ul și cartea de Minix, ceea ce l-a pus într-o poziție delicată, pentru că niște domni l-au întrebat de unde vine pachetul din Olanda, că eu acest străin, nu știu ce. Tannenbaum a înțeles că trebuie să procedeze într-un anumit fel, în fine. Partea întâi a interviului este despre Tannenbaum și se termină cu scrisoarea dată lui Nelu de către Tannenbaum și care era în garaj și care a căutat-o special să o pună pentru mine. Deci așa se termină. Asta e partea a doua care vorbește despre folosirea TCP/IP-ului, atenție, înainte de 1990, la Măgurele. Vă rog să urmăriți cu atenție acest mic interviu.
Prin 1986 s-a pornit un proiect de fapt la început la Institutul de Fizică și Inginerie Nucleară și Fizică Teoretică pentru crearea unei rețele de calculatoare între diferite departamente. Nu știu dacă toată lumea știe că de fapt la IFA erau mai multe institute locate cu locații diferite și care nu erau, bineînțeles că nu erau conectate cu nimic. A apărut acest proiect. În legătură cu acest proiect, IFA, pentru că avea un statut mai special.
Clădirilor și a modulelor de acolo.
Da, și care a fost la început sponsorizat de Departamentul de Fizică Teoretică, împreună cu directorul Pascovici, dar în cadrul acestui proiect s-a primit un program al Națiunilor Unite pentru Dezvoltare, în care s-au alocat, nu mai țin minte exact suma de bani, era ceva între 3 și 5 milioane pentru acest proiect. Ca parte a acestui proiect s-a decis să se formeze o echipă care era mai mare, dar o echipă de conducere, dacă vrei, de 3 indivizi, între care am fost și eu. Șeful era un cercetător destul de renumit, Gheorghe Costache, celălalt partener al meu era Șerban Constantinescu, care, de fapt, după ce am plecat eu din România, a continuat să îmbunătățească internetul, să adauge foarte mult după 90 și așa mai departe. Deci Șerban Constantinescu este și el un nume care a trebuit reținut în istoria internetului în România. Deci am primit acești bani și a trebuit să ne gândim ce să aducem, da? E clar că ne-am gândit, o să aducem Unix, nu mai folosim RT11, nu mai folosim RSX și vom aduce Unix. Următoarea întrebare a fost, ok, în general, IFA era interesată să aducă PDP-ul și fax-ul. Mai erau...
Bineînțeles, toată lumea folosea asta.
Da. Dar noi am decis să facem o cotitură care a fost puțin influențată și de către cei de la Automat, că Irina Țepuș și Moisa. Am zis, vrem să aducem servere bazate pe procesoare Intel. Deci, sistem de operare Unix și procesare Intel. Problema a venit, ok, vom aduce asta, dar ce fel de rețea vom construi? Și aici iar o poveste interesantă, pentru că nu am reușit să...
În afară de niște experimente la ICI cu plăci Ethernet și cu o rețea care au făcut ei acolo artizanal, eu nu știu alte lucruri.
Deci, hai să spun toată povestea asta, pentru că, de fapt, partea asta de rețea, era clar pentru mine ce trebuie să aducem, TCP/IP și Ethernet, dar ceilalți doi parteneri ai mei aveau niște dubii și, de fapt, Gheorghe Costache, șeful, a avut o atitudine corectă, după părerea mea. A zis, hai să mergem să întrebăm pe la mari specialiști din România ce zic și ei. Și bineînțeles că am fost la toate casele de renume, nu vreau să le mai spun, bineînțeles, Facultatea Automatică, aici, ITC, fabrică și mai departe, și am întrebat ce tipul de rețele de calculatoare trebuie să aducem. Ceea ce este interesant este că, de fapt, nimeni n-a menționat TCP/IP. Deci nu vorbeam despre internet și așa mai departe. Deci, după ce ne-am întors din acest pelerinaj, să-l numim așa, am avut un dubiu foarte mare. Ce faci? Nimeni nu recomandă asta. Până la urmă am reușit să-i conving pe ceilalți doi parteneri ai mei că TCP/IP este și internetul sunt modalitățile de a merge mai departe. Acum, decisesem în punct de vedere teoretic care este configurația, trebuia să facem rost de niște sisteme.
De calculator.
Și aici a fost o altă mică problemă. Bineînțeles că ne-am dus la reprezentanțele firmelor străine care erau acolo, Hewlett Packard, Rank Xerox, pentru a căuta o configurație. N-am găsit-o.
Noi la IRUC lucram cu HP-ul, deci HP-ul, venea cu noi când era orice. Eram singurii colaboratori ai HP-ului și Xerox-ul lucra numai cu IRUC-ul și ei mi-au trecut prin mână calculatoare Xerox, dar toate nu aveau placă de rețea. Pentru că plăcile de rețea erau sub embargo COCOB.
Exact.
Foarte clar. Deci, perioada aia
asta era
embargo pe Ethernet.
Asta era marea problemă. De fapt, din cauza asta începusem să fac și eu analizor multicanal, că și ăsta era sub embargo. Dar, oricum, deci am mers la Rank Xerox și mi-aduc aminte că HP era pe Batiște, avea un birou acolo.
Da.
Bineînțeles că, într-un fel, ne-au spus, este sub Qualcomm, dar poate reușim să facem ceva, dar au niște prețuri exorbitante. $200-300 de dolari un server și așa mai departe. Deci, a trebuit să recurgem la niște metode necanonice ca să facem acest rost de aceste calculatoare. Nu o să spun detalii, pentru că era vorba de a de a trece peste aceste POCOM, aceste probleme cu embargo care se găsea România. Deci, în cele din urmă am găsit o firmă australiană care s-a oferit să ne aducă exact configurația pe care am vrut. Mi-aduc aminte și acum firme australiane, era vorba de, se numea Laptam. Deci, această firmă australiană cumpăra componente din Taiwan și le asambla în Hong Kong și găsea modalități de a evita acest embargo POCOM.
Totul până în 89.
Deci, aceste discuții pe care le-am avut cu specialiștii din România au fost prin 1987. Am ordonat calculatoarele, cred că tot cam așa, prin 1987. Am primit primele calculatoare, că au fost în mai multe serii, primele servere Unix cu Intel. Nu mai mi-aduc aminte câte memorie aveau, dar mi-aduc aminte frecvența 33 de MHz. Iar interfețele internet erau de 10 megabits pe secunde. Era o chestie extraordinară.
Cablu de acela rotund cu axial, nu?
Da, bineînțeles, cu cablu cu axial. Deci, am instalat primele calculatoare și le-am conectat la început în interiorul departamentului de fizică teoretică, unde era centrul de calcul cel mai mare, în anul 1988. Deci pot să spun că prima rețea locală, hai ca să fim corecți din punct de vedere tehnologic, prima rețea locală bazată pe tehnologie internet a fost în cadrul centrului de date al fizicii teoretică de la IFA, după care
foarte interesant. Eu am fost convins că prima rețea TCP/IP care a funcționat este cea de la Politehnică din 91, 90-91, când au venit HP-urile, Hewlett Packard-urile și donația de la Darmstadt. Dar iată că aflu lucruri noi.
Deci, este ușor de înțeles de ce nu toată lumea știa despre această rețea. Pentru că a fost făcută, aducerea de echipamente a fost făcută puțin
exact,
cu manieră delicată, ca să spun așa.
Da.
Dar erau persoane cu funcții din industria de calculatoare românească care știau, nu foarte multe, erau...
Nu, eu de exemplu n-am știut, deși cu Irina Atanasiu am lucrat la testele de memorie de la Felix PC. Și pentru că noi lucram în laboratorul nostru de dezvolta diagnoză pentru calculatoarele românești, am ajutat la Felix PC, la proiectarea lui Felix PC.
Acum, așa cum îți spun, înțeleg de ce nu s-a vorbit foarte mult, pentru că erau niște chestii încă sub embargo. Da. S-a ținut acest efort, s-a ținut puțin sub umbrelă, dacă vrei, ca să nu fie popularizat și să nu se creeze probleme de altă natură. Dacă să venim la partea tehnică, deci a fost instalat acest sistem, încet a fost extins. Eu, în ianuarie 90, am plecat imediat la CERN și practic între 90 și 92 am stat la CERN, la Universitatea din Londra și la un institut în Germania, din Darmstadt. Deci,
eu m-am întâlnit cu tine când ai avut tu teza, când ai susținut teza în sală 22, că eu eram interesat pentru mine, că începusem și eu să lucrez la doctoratul meu.
Mi-aduc aminte,
făceam diagnoză de rețele, făceam diagnoză pentru sisteme RISC multiprocesor, redundanța software-ului și după aia am trecut la diagnoză de rețele pe măsură ce s-a dezvoltat partea de rețele pe scară largă. Da, și internet.
Da, mi-aduc aminte că ai fost la susținerea mea de doctorat. Țepuș, Moisa, Irina, bineînțeles Pascubici a fost acolo, dar de ce vreau să spun în legătură cu internetul este că eu fiind plecat ca să-mi practic să fac toate implementarea acestei teze de doctorat și diferite teme de cercetare. M-am deconectat puțin de ce se întâmpla în țară, în domeniul internetului la IFA, dar știu că Șerban Constantinescu și cu profesorul Pascovici au conectat IFA la CERN prin anii 1990-1991. A avut nu mai țin minte, probabil că a fost 4800 de bits pe secundă, nu mai țin minte care...
4,8 kilobits pe secundă. Da.
Da, cred că asta a fost prima dată, dar ei au început să lucreze. Eu, fiind plecat în acești 2 ani, practic, n-am stat în țară decât vreo 3-4 luni,
deci
am cam pierdut...
de poveste o știu ei mai bine dacă aș vorbi cu ei, să zicem. Da.
Exact, dacă ai vorbit cu ei, dar de fapt, profesorul Pascovici a publicat despre aceste eforturi în mai multe cărți ale Academiei. De asemenea, cred că în 91-92 sau 92 a fost o conferință internațională la care eu îi spun COCA, pentru că ne cunoaștem foarte bine, COCA și Paul Cristea de la Facultatea Automatică au fost la o conferință în Japonia și au vorbit despre implementarea...
Să zic ce mi s-a întâmplat mie în 1994, la INET-ul 94 de la Praga, când m-am cunoscut cu George Sadovski și cu Vinton Cerf și cu John Postel. Mi-au spus că la Kyoto 92, la primul
exact, la Kyoto, da.
INET 92, s-a prezentat ceva despre institutul de fizică, atunci mi-au zis ei, și Steve Roos mi-a zis că atunci el s-a implicat foarte tare, împreună cu un fost ambasador american aici în România, Barnes, la comunicațiilor internet din România. Eu nu știam despre la ce se referă, eu nu văzusem lucrarea aia și nu cunoșteam lucrurile astea și am rămas foarte mirat atunci.
Deci eu am în dreapta mea un monitor în care am prezentarea lui Coca pe care a făcut-o la aniversarea, am uitat nu știu câți ani de la Institutul de înființarea Institutului de Fizică Atomică și spune așa că Harry Barnes Jr., care a fost ambasador,
exact.
și Steve Roth, cu o donație de la Carnegie Mellon University, au realizat, nu spune anul aici, o conexiune telefonică cu ICI și Institutul Politehnic, prin BitNet, mai spune aici că în 2000 avea 1 gigabit pe secundă, bla 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 și așa mai departe.
Aici se vede unde s-a ajuns. CERN-ul e legat la 100 de gigabits pe secundă cu măgurele și slide-ul ăsta este foarte interesant pentru că vedem toată evoluția. De la 8 linii pe coral până când s-a ajuns la viteza care este acum. Ei au nevoie foarte mult la acest institut de această conexiune și înțeleg perfect cum s-a realizat. Nu am știut de lucrurile astea și mi-a făcut o deosebită plăcere să vorbesc cu Nelu despre această treabă. Deci, el spune că proiectul ăsta și inclusiv discuția cu Tannenbaum i-au schimbat complet viața, i-au schimbat cariera. S-a angajat după aceea la laboratoarele Bell și a lucrat la sistemul de operare a AT&T-ului pentru rutere vreo 8 ani. Deci, nu prea a zis lucrurile astea până acum. În fine, noi am avut așa o discuție ca între doi bătrânei, cum se spune, despre lucrurile acestea. Slide-ul respectiv l-am lăsat mai mult timp, adică cam 1 minut, ca să vedeți toate detaliile. Evident că acest interviu o să-l punem undeva pe site și după asta o să fie accesibil inclusiv partea întâi, aceea cu Tannenbaum, care se termină cu o scrisoare trimisă de Tannenbaum lui Mihai Nelu. Cred că mai e o bucățică, dar m-aș opri aici.